Good morning, students. Uh, we have already studied structural isomerism in coordination compounds. And then second type of isomerism which is shown by coordination complexes is stereoisomerism or space isomerism. This stereoisomerism or space isomerism is further classified into two classes. One is optical isomerism and the second one is geometrical isomerism. So today we will discuss geometrical isomerism. Now we will discuss about geometrical isomerism. First of all, we have to understand what are geometrical isomers. So geometrical isomers, they are different compounds which possess the same molecular formula, but they differ in the way the various ligands or groups which are attached to the central metal atom or ion, they differ in their orientation. So the compounds which differ in the orientation of groups or ligands attached to the central metal atom or ion are known as geometrical isomers, and the phenomenon is known as geometrical isomerism. Now, this type of isomerism is found in heteroleptic complexes. To remind you, what are heteroleptic complexes? Heteroleptic complexes are those coordination compounds in which two or more than two types of ligands are bonded to the central metal atom or ion. Now, this type of geometrical isomerism does not exist in complexes having coordination number 2 and 3. And if we talk about coordination number 4, there are two possible geometrical shapes. One is tetrahedral and another one is square planar. In tetrahedral complexes which have coordination number 4, also this type of geometrical isomerism is not seen. It is very important question which comes in the board, which comes in the exam. Why tetrahedral complexes do not show geometrical isomerism? Sir, the ligands when present in the tetrahedral orientation, tetrahedral shape, their position is always same with respect to each other. Okay, tetrahedral complexes, they do not show geometrical isomerism. Reason? Because the positions of various ligands with respect to each other remains the same. So tetrahedral complexes, they do not show geometrical isomerism. And what about complexes which are having coordination number of 6? In complexes which are having coordination number of 6, they show geometrical isomerism. So we will discuss geometrical isomerism in case of square planar complexes having coordination number 4. We will discuss geometrical isomerism in octahedral complexes of different types. Now let us understand geometrical isomerism in square planar complexes. What is a square planar complex? When the metal atom is present in the center and the ligands, they are directed towards the four corners of a square, right? Now this type of isomerism, square geometrical isomerism, is seen in square planar complexes of the type mx2 L2. Now what is M? M is the metal atom or ion. And what is X and L? They are unidentate ligands. Two ligands X2, two ligands, they are of one type. L2, two ligands, they are of other type. Now what example we will discuss? We will discuss the example of a complex of platinum cation having two ammonia molecules as ligands and having two chloride ions as ligands. Now look at the figures. On the left hand side, platinum is present in the center and two chloride ligands, they are present on one side and they are present adjacent to each other. And the other two ligands, that is the two ammonia molecules, they are present on the other side adjacent to each other, right? And such isomers, they are known as cis isomers. Now what is a cis isomer? A cis isomer is that isomer in which the two similar ligands, they are present adjacent to each other. Now let us see the second example, that is trans isomer. Now in this, platinum is present in the center, and the two chloride ligands, they are present opposite to each other. Similarly, two ammonia molecules, two ligands of ammonia molecules, they are also present opposite to each other. So such isomers, they are known as trans isomer. Okay, now what is a trans isomer? Sir, that isomer, that geometrical isomer in which similar ligands, they are present in places opposite to each other. That is why this type of geometrical isomerism, which is shown by complexes of mx2l2 type complexes, is also referred to as cis trans isomerism. So this is an example of cis trans isomerism in square planar complexes. Now we will discuss geometrical isomerism again in square planar complexes, but of the type MABXL type. Now what does it mean? M means metal atom or ion, and then there are four ligands which we are denoting by A, B, X and L abbreviations. Okay, that means in this case the square planar complex is there, but all the four ligands, they are entirely different. So what example we are going to take? We are going to take example of a platinum complex. It has got four ligands bonded to it. Right? It has got four ligands bonded to it. One is ammonia molecule, one is pyridine molecule, one is hydroxylamine ligand, and one is nitro group. Okay, so when you will draw the structures, you will get three isomers. Two isomers we will call it as cis, okay, and one will be trans isomer. Sir, how to draw the diagrams? You write the platinum in the center. Look at the first two figures, first two diagrams, and on left hand side you write the same ligands, ammonia ligand and then nitro ligand. In the second diagram also, above is the ammonia ligand and below is the nitro ligand. But how these two differ? In the first one, pyridine is written above, whereas in the second one, pyridine is written at the bottom. Okay, so pyridine and hydroxylamine. In the second case, above is hydroxylamine and then pyridine as a lower position. So these two isomers, they are called cis isomers. Why? Because on the left hand side, the same groups, nitro group as well as amino group, similar groups, they are occupying the same site. So these are called cis isomers. And then the third one is trans isomer, where that amino ligand as well as the nitro ligand, they are present opposite to each other, whereas hydroxylamine and pyridine, they are also present in position exactly opposite to each other. So it is called trans isomer. So when we write the structures of a square planar complex of MABXL type, we get two cis isomers and one trans isomer. Okay, please practice it. After discussing geometrical isomerism in square planar complexes having coordination number 4, we will discuss geometrical isomerism in octahedral complexes whose coordination number is 6. So in this we will discuss geometrical isomerism in octahedral complexes of the type mx2l4 type. That means there is a metal atom and two types of ligands are present. Two ligands are of same type and four ligands are of different type, right? And the second example which we will discuss is in the ligands mx2ll2 type. What is LL? LL means one didentate ligand. So that means in this type mx2ll2 type, there is a metal atom and two ligands, unidentate ligands of one type and two didentate ligands. And the third example which we will discuss in octahedral complexes will be Ma3B3 type. One is metal atom and 3 legends of one particular type and 3 legends of the second type, right? So we will discuss geometrical isomerism in octahedral complexes of type MX2L4 type. What does it mean? It means that there are two types of legends. One is represented by X. There are two legends of one type, and the another legend is represented by L. There are four legends of this type. So what example we are going to take? We are going to take example of a cobalt complex. It is having 4 ammonium molecules as legends and 2 chloride ions as legends. Now let us look at the structure. Now you see, towards the 4 corners of a square, the 4 legends are directed, and 1 legend is present above cobalt atom and 1 legend is present below cobalt atom. Right? In the first diagram, the 2 chloride legends, they are present adjacent to each other, close to each other, and the remaining 4 ammonia molecule legends, they are present on the other remaining 4 positions. So this is the example of a cis isomer. In the second figure, you have a look. The 2 chloride legends, they are present opposite to each other. One is present above the cobalt atom and another one is present below the cobalt atom. And the 4 legends, they are directed towards the 4 corners of a square. So this is trans isomer. So what you have understood is geometrical isomerism, that is cis and trans isomerism, shown by complexes of type MX2L4. Now we will understand geometrical isomerism in octahedral complexes of the type MX2LL2 type. It means that with the metal atom, 2 legends, unidentate legends X2, they are bonded, and 2 didentate legends, which are represented by LL in bracket, they are bonded, right? So let us see geometrical isomers of this type. So example which we are taking is, it's a complex of cobalt to which 2 unidentate legends, that is chloride legends, they are attached, and 2 didentate legends, ethane 1,2-diamine legend, they are attached, 2 in number. Okay. So look at the first figure. Now you see this is ring type structure, and in the ring type structure in the center we have written En. We can also write the total structure of ethane 1,2-diamine, but for simplicity we represent it like this. In the same way, oxalate, if present, that is also represented like this. Instead of En, we write OX. Now in the first example on the left side, that is cis isomer, what is there? The 2 chloride ions, they are present on the same side, whereas in the other one, the 2 chloride legends, they are present opposite to each other. The first one is therefore known as cis isomer because similar legends, chloride legends, they are present adjacent to each other. And in the second one, trans isomer, the 2 chloride legends, they are present opposite to each other. Okay, so geometrical isomerism in MX2LL2 type of complexes. Now the third type of geometrical isomerism, which is shown by octahedral complexes, is shown by complexes of type Ma3B3. That means when to a metal atom or ion, 3 legends of one type, they are bonded, and 3 legends of another type, they are bonded to the metal atom or ion. Now example which we will take, that will be of a cobalt complex having 3 ammonium molecules as legends and 3 nitro groups as legends. Now this type of octahedral complexes, they show an isomerism which is very important. We call it as Fick and Mer isomerism, facial isomer and meridional isomer. Now in an octahedral complex, there is a square which forms a base, and above the square there is a pyramid, and below that square there is a pyramid, then we get the shape of an octahedron. So there are 8 faces of the octahedron. If 3 similar legends, they are occupying the 3 corners of a face of octahedron, we call it as facial, we call it as Feck isomer. And if the 3 similar legends, they are present, they are occupying the 3 position of that square, of that meridian position, then we call that isomer as meridional. We call it as meridional because the 3 similar legends, they are occupying the position in meridian. Okay, you will see the diagram in the next page. On the left hand side, I have represented the facial isomer, that is Feck isomer. Look, there are 3 ammonia molecules which are occupying the 3 corners of a face. Right on the left hand side, there are 3 ammonia molecules, ammonia legends, they are present at the 3 corners of a face, while all other legends, they are present in the other positions. So this is facial isomer or Feck isomer. Now look at the figure which is present on the right hand side. It is meridional isomer. Now the 3 ammonia molecules, they are present on the 3 positions on the meridian. That means the square which forms the center of this octahedron, the 3 ammonia molecules, the 3 similar legends, they are occupying the 3 positions of this meridian. So this type of isomerism is known as meridional isomerism, meridional isomer. So the isomerism shown by this type of complexes, that is Ma3 and B3 octahedral complexes, is Feck and Mer isomers.